오케이. 수업은 휴일 없이 네네. 이번 연휴는 휴일 없이 그냥 진행합니다. 물론 뭐 안 오셔도 상관없습니다. 이번 목요일에 실습, VA 실습과 영어로 할게요. So during the 추석 기간, the holiday season, we will have the practice session and the theory session as usual. So as usual, as always, you don't have to come. We will upload the videos after the session. So if you have somewhere else to go, no problem. If you happen to be around, sure, please come. All right, so I think we should begin. We have a lot to cover today, so hopefully within an hour and a half, we can cover. So variational autoencoder. So as you can see, it's an autoencoder, but it's an extension of the autoencoder that we learned last week. So hopefully you have complete understanding of what an autoencoder is. If you don't, you can ask questions during the class anytime you want. So 4 things we'll talk about. So with an autoencoder, with a trained autoencoder, can you make it generate images like samples, for example? So generative autoencoder, and then go into variational inference before we go into variational autoencoder. So I'm going to call variational autoencoder VAE. So before we dive into VAE, we need to check on the concept of variational inference, which is very important. So we'll talk about that. So after that, we'll talk about VAE, and then one more thing while training VAE. So VAE is theoretically a very sound, very beautiful framework, but when you want to train it, there's a bit of a catch. So we'll talk about that. So generative autoencoder. So we all know, hopefully we all know that the basic concept of autoencoder, we have a compression stage or the encoding stage, and the decompression or extraction stage, or so-called decoding stage. And the compressed vector representation in the middle, which we call Z, is usually called either code or latent variable or latent representation, right? So that's the setup. And the simplest form of autoencoder was just one layer in each side, one layer, a neural network for the, well, not neural network, but one layer like nonlinear transformation, nonlinear here, F, one layer nonlinear transformation from the encoder side and on the decoder side as well. And we typically use the MSE loss, the mean squared error loss. And yeah, because of the information bottleneck here, if we use a considerably smaller sized Z compared to X, so in X, what was it? It was 784, right? So 784 dimension here, and if it's just 4 dimension here, there's a severe bottleneck. And because of that, the autoencoder had to learn only the distinguishing features among the samples so that it can reconstruct with high quality, right? Just we had a whole comparison between the autoencoder and the PCA. And yeah, we briefly touched upon the visualization. So once we compress, or once we learn the latent representation of each sample, for example, here, this one could be mapped to this 4-dimensional vector here. This one could be mapped here. This 5 could be mapped here. And during visualization, we kind of saw that these two, because they're both ones, these two are placed in the proximity of each other, like close to each other, as opposed to like, for example, like 1 versus 5. Like 1 is like way up there, 5 is like way down there, something like that. So the question is, and also, yeah, we looked at the latent space. So we talked about how 1s are all here, but they're like 5 and 4 and 7, they're all entangled in this region. So it's really hard to like completely separate one from the other. Right, so that was it. And the question is, can we generate new samples? So we have a trained autoencoder. So the latent space of autoencoder looks like this. And based on this finding, I mean, this is just an approximation, because in real, the actual autoencoder, the latent space, the size of the latent space was 4, right? So, but because we wanted to scatter plot it, we downsized it to 2 using either PCA or t-SNE or UMAP. So this is even an approximation. The actual latent space of the autoencoder with the latent space size 4 doesn't exactly look like this. This is just like a projection to the 2D space. But anyhow, so once we know that, can we somehow generate new samples? And for example, one simple idea could be For example, if you wanted to generate a new sample of digit 1, then what you can do is you can pick one actual sample here. So this is an actual sample of digit 1, and this could be like, let me this could be like zi, right? So this is some z. This is a the true identity of this dot is a 4-dimensional vector, which is a compressed representation of actual digit 1. So we take this z, and then if we slightly add some noise and then create a new one right next to it, like this, then hopefully, or more likely, that this red arrow, this red dot here, which I'm going to call zi prime, is more likely to be a digit of 1 rather than being 2 or 4 or 7, because it is right next to the 1, it's going to be a 1, right? So that's one way to generate a new sample. So that's one way to do it. And if we move on, another way is sampling random points from this area to generate image of 1. So there's a lot of ones here. Like these are all ones. I think these are all ones. So we just pick whatever. We just pick this one, and then that's a 1. And if we pick this one, this is a 1. I mean, but that wouldn't be generating a new sample. That would be just copy pasting, because we're exactly using the same z's that we already know that they're there, right? So, or we could treat this as some Gaussian distribution, and then, I mean, it's not a Gaussian distribution. It doesn't look like a Gaussian distribution, but we can just imagine that this is a Gaussian distribution and just sample this random dot here. Or we can even do a little more informed stuff. So a little bit more like, for example, there are 2 dots here, one here, then we can do an interpolation. Like there could be dot here, dot here, dot here. So we're assuming that since this is a 1 and this is a 1, then anything between the two is probably a 1. So that's enough. So there are a lot of tricks we can use on top after we've trained an autoencoder, and then to try to generate a new sample. So those were just a few. So yeah, perturb a unknown z, perturb a known z, or sample from a region, and yeah. But both are not guaranteed to work. Like there is no guarantee that it'll always give you what you want. For example, if you perturb from here, then you won't, there's no guarantee that either you will get a 4 or 5 or 7, because they're all intertwined with each other. And I mean, this region is pretty safe, but like here or here or here, like 8 and 3, there's no guarantee. Okay, I'm gonna have to mute everybody. And even if you perturb a known z, like how like large of perturbation would you want to add? Like this much? Or very small amount. If you add a very, very small amount of noise, then that won't be generating a new sample. It's just a slight variation of the digit that we already know. So there's actually, I prepared a example like way back in the past. So what I did is I took a trained autoencoder. So this is an autoencoder trained on MNIST. I go trained on MNIST, and I just randomly picked a 9. And then its reconstruction is this. So it's a little bit blurrier. So this is X. Oops, let me better use this one. So this is X. This is X prime, the reconstruction. And you can see it's a little bit blurry on this side, but still it looks good. We can tell that it's a 9. So what I did is I took this, so there should be a Z somewhere here, right? So I took this Z, and then I perturbed it. And if you perturb it with a Gaussian noise, mean of 0 and standard deviation of 0.5, you would get samples like this. So samples like this. So they are pretty much the same. Like with a very small amount of noise like this, then like compared to here and this guy, and this guy, it all looks like pretty much the same. Like it's not a new style. It's like, basically the same thing. If you add a stronger noise, like standard deviation of 1.0, then you start to see some differences. So there's a bit of a skew here, and I guess this is pretty much similar. This one's a bit new. So you know the circle in the 9. There's like a cutoff here. So at least this guy and this guy looks a little bit different, but the style is pretty much the same. Like the thickness, the angle of digit 9, like it's pretty much the same. So you can see that just by simply perturbing an existing sample, you won't get a new thing like this. You won't get a new digits like these. So unfortunately, that can't be done because all you're doing is just perturbing. But this is what we would like to do. Like we want to generate new 9s like these, like as diverse 9 samples as possible. Right. So that was kind of a motivation behind, like, I mean, so you can see that with an autoencoder, you can still like kind of generate samples, but it's not a true generative model because you're just using tricks to generate new samples. So before we dive into VAE, we're going to take a look at the variational inference, which is a very widely used trick for in machine learning, and it would be a good opportunity to get a concrete understanding of what the whole idea is about. So, any questions so far with the autoencoder and using it to generate new samples? Okay, so I'm guessing there are no questions. All right, so we have to first talk about the posterior distribution. So the whole idea behind variational inference is that we want to know or estimate the posterior distribution. So if you are familiar with Bayesian principle, P of, I'm going to use X and Z because there's Z and X here. So P of Z given X is what? It's a likelihood, X given Z, times prior, PZ, divided by PX, the evidence, right? Or sometimes this is also written, okay, I should have used the space a little bit more sparingly. So PZ, integral or sigma, PX given Z, PZ, DZ, right? So it's either this form or this form, but they're the same thing, right? So this is Bayesian principle, and we call this the posterior distribution. So what we typically let's think about like an actual sample, news articles. So a news article has a topic. So if you go to a Naver News or Yahoo portal or wherever, there's typically a news portal, and there are categories like politics or society or international affairs, science, celebrity, sports, right? So each news article has a topic, and so that topic, we can assume that topic is the Z, and we can assume the news article itself as an X, right? And what we want to do is, what we assume is that before journalists or writers write the actual X, this is the end product, right? So the news article itself is a product. So before writers or journalists write a news article X, they have a certain, like a topic in their mind. Like, I'm going to write a politics article. I'm going to write a sports article. I'm going to write a society article. So that topic or the category is the Z. And what we want to do is we only can observe the X. We can only read. That's all we can do. Like, I'm assuming that there is no category or tabs in news portals. We can only look at the news articles. And what we want to do is we want to infer the hidden Z, the hidden topic. So that's the whole setup. So we assume that X is generated based on Z, and we don't have access to Z. So what we would like to do is, by observing X, we want to infer Z. So that's the whole estimating or inferring the posterior distribution, like this. So we have X, we have access to X, and we want to know the distribution of Z, the topic of in the case of news articles, the topic distribution of Z. It could be like 70% sports, 20% celebrity, 10% society, something like that, when you look at an actual X, the news article. So this is the typical plate notation. So the dark one is the observable variable, and the transparent one is the non-observable hidden variable, or the latent variable. And there are n samples, so that's the whole setup. And typically, what we know is that what we assume is that the Z itself, the topic distribution in the news article case, or just in a purely abstract form, the distribution of the latent variable follows certain distribution, obviously. So it follows like in the case of if Z is continuous, it could be like a PZ, could be a Gaussian distribution. If we're sticking to the news article example, then Z could be a multinomial. Z is like a topic, so PZ could be a multinomial distribution, something like that. And we assume that we have access to this likelihood function. Like if the Z is fixed, then we kind of know that how X is generated. Like, like if the topic was set to politics, then you kind of you assume that you know the distribution over like words. Like if the topic is politics, then the multinomial distribution of words is like, I don't know, like 국회, no, sorry, White House 5%, Obama 2%, Trump like 3%, something like that, basically. So we assume that we do know these stuff. And what we want to do is based on these assumptions, we want to do this. We want to know this. We want to calculate the posterior distribution. Oh, by the way, the whole thing, these like notations and the figures are borrowed from this very nice blog here. So if you have time, you can visit there. So yeah, just as I said, like if we're talking about news articles, the Z could be the topic. If we're talking about MNIST images, for example, here in the autoencoder, assume that we were in the autoencoder, let's assume that we were compressing and decompressing MNIST digit images, then the MNIST images themselves could be the X, and the latent representation, the Z in the middle of the autoencoder, that could be our Z. So that's like, there are a lot of different, it's a very general framework. The PXZ, like this is a whole very general framework. So you can apply it to many, many different situations. Right, so typically what we would like to do is this, using Bayesian principle. So as I said, it's either this or this. And I was just writing this down as PX given Z, PZ, instead of the joint distribution. Because as I said, we were assuming that we do know PZ, we do know PXZ. So if you convert this term, if you convert this term to this term, then basically we now have everything that we need to know to infer this. So because we know this, we assume that we know this, we assume that we know this, then we know this, but then we know this, then all we need to do is just figure out how to do with the integration. Then we can calculate the equation for PZ given X, the posterior distribution, which was our end goal from the beginning. But the problem is that this is usually intractable, because if, for example, Z is a continuous variable, like in our autoencoder case, like in our autoencoder, Z was a 4-dimensional continuous variable. Z was like this, right? So there's like an infinite possibility, and there's no way you can, reasonably, in a reasonable amount of time, search through the entire space, the DZ, right? So it's intractable. And if we're talking about like discrete variables, like where Z is the news article topic, and if there are only like 5 topics in news articles, then this will be converted to sigma. So that is totally doable. Like you just need to do a for loop over 5 times across different topics. But if that Z is still like very large, like the entire word, then it's going to be 3,000, 30,000, 100,000, maybe millions, then it's still intractable. So it's not always the case that you can nicely convert this into this in an analytical manner. So that's the problem. So that's where the problem is. So what we would like to do instead is, I mean, there are other ways to solve, like handle this. You can do like a Monte Carlo estimation and that kind of stuff. But we're going to talk about VI, variational inference. So we're going to do that. So in the spirit of VI, variational inference, is that, well, we don't know this, and we don't know how to handle this. So we're not going to do any of this Bayesian thing, and we're just going to approximate PZ given X, the posterior distribution, with some new function, QZ, that I am familiar with. For example, Gaussian distribution. So what we do is, we don't know the true PZ given X, but what we are going to do is we're going to use a known function, QZ, to approximate this. And because of that, QZ must be a manageable, like known function, such as Gaussian distribution. So if QZ given X, if PZ given X happens to be like, like a Gaussian-like distribution, this could be a very good choice. But if PZ given X is like the true distribution looks like this, then like, you know, like a lot of modes and totally non-Gaussian, then using QZ, which is a Gaussian shape. But so if we assume that QZ is Gaussian, then all we have the freedom of is the mu and sigma of this distribution. So all we can do is just tune, or, you know, like adjust the values for mu and sigma so as to closely approximate PZ given X as much as possible. But if the PZ given X looks like this to begin with, then all you can do is just like this. This is your best. And it's not this is not an accurate approximation, because there's like gaps, there are gaps here and here and here and here, like, you know, so it doesn't always work, but, you know, it's something that we can do if we don't want to like sample using Monte Carlo simulation, right? So far, is the motivation clear? You have to keep this motivation, the big picture, in mind as we move forward. All right, so no question. I'm guessing that's a good sign. So so as I said, we want to approximate PZ given X, the unknown distribution, with a known function QZ, and that means that we don't want them to be too different. We want these two to be as similar as possible. So the go-to choice for that, like, you know, calculating the difference between two probability distributions, is usually Kullback-Leibler divergence. So KL divergence. So the equation of KL divergence is like this. So this is just a definition. So you have Q and you have P. So P is this guy, so this guy, and Q is this guy. And this DKL is the quantifies the difference between the two. So the definition looks like this. And note that DKL is not symmetric. So there's another DKL, which is the PQ, and this is actually a bit more like a popular or more often used form compared to QP. Like P is the one that we know, Q is the one that we want to use to approximate P. So if that's the setup, we usually go with this PQ instead of QP. But in variational inference, we stick to this. And if you want to use PQ, you get something called expectation propagation, which is another estimation trick. But in variational inference, we stick to QP. So QP, and they are not symmetric. If you look at this, like the Q being here, then there's QZ here. So if P was here, then you would assume that P and P would be here instead, and Q being here. So they're definitely not symmetric, right? Right. So yeah, and we're assuming that Z is discrete variable. If Z was a continuous variable, then it would look like this, like an integral sign. So far so good, and we have some terms shuffled around, so it looks a bit complicated, but it's not complicated at all. What we do is, so we start with this. What we want to do is we want to minimize KL divergence, because minimizing the KL divergence means that the QZ and PZ given X are as similar as possible. Like they're like similar. So the minimum value of DKL is 0. The 0 is when these two are exactly the same, then DKL becomes 0. And any other than exactly being same, it's a positive value. So we want to minimize this term. So, and we start from here, and what we do is we break this term into like these two, right? So it's just likelihood broken into a joint distribution and a PX. So that's it. And then after that, we break this into two parts like this, because there's a log function here, so you can put log PZ here and log QZ here and log PZ here, and that's it. So that's it. And there's one more difference, so one more change. We take this into here and also here, so we get this. So this guy is here, right? No biggie, no big thing. And then when you go from here to here, you can see that this is no longer like there. So this is the definition of EQZ log PX. Let me write it down a little bit more. So because this is a expectation, so the Q is a probability distribution. It's a PDF, and there's an expectation. There's like a summation form. So this is exactly EQZ expectation over log of PX, right? So this is this. And because if you look at PX here, it doesn't have anything to do with Z. Like this, like completely just different story. So you can just throw this away. So that is why you get this guy. So, and then after that, like you can just treat this as an expectation again, expectation. So that's it. So there's like you start from here, which was this, and then you arrive at this place. There was a question from Cedric before fixing QZ as a Gaussian distribution, and instead of calculating all of the integrals, is there any way to do some kind of random sampling to have us inside of which distribution we should pick for? Actually, so that means that you need to study PZ given X. So we assume that there's like a generation function for PZ given X, and I'm not sure there is. Like you need to have a formula in order to sample from PZ given X, or you need to have like a whole lot of data to. Actually, yeah. I don't think so. Yeah, I think it's a very tricky situation. Like you don't know if you knew the equation, then you don't need all this trouble, right? So you don't know the equation, so it would be very hard to like generate samples from PZ given X. And if you just look at the data, then well, you don't know the Z. Like Z is like your imagination. It's a topic in your head. So I'm not sure how you would sample. I mean, there could be a way, but off the top of my head right now, I'm not really sure. But it is a good idea. Like if there was a way to explore the space of PZ given X, and then if we could see, like if it looks like this, or if it looks like this, or if it's bimodal, like if you have a good idea, you could choose a QZ with a little more information. Sure. All right, so we were here, so we are now here, and then we move on to the next slide. So we start. So this is it. This is the same thing as this guy. So same thing. We just take this. And then we move it over here. Then the log px would be on one side, and the other thing would be on the other side. So this is what that is. So log px on the one side, and dkl is where we started from, and this guy is just this guy moved over here. So that's it. That's it. So we call this part evidence lower bound, elbow. If you heard about this term elbow, then this is what elbow is. Like you minimize the elbow, you maximize the elbow. Like this is the so-called elbow. So you started from the definition of DKL, and we moved some terms around that. We rephrased it like this, and then we take this guy here, and then all we're left with is this. And still, remember, what we want to do is we want to minimize this guy. But instead of doing that, what we're saying here is that maximizing the elbow leads to minimizing DKL. So we don't directly minimize DKL. We don't do that. Instead, what we do is we maximize the elbow, because that will lead to minimizing DKL. So we maximize this guy. So the elbow term includes the sign. So please don't forget that. So this elbow term. So when you maximize this, we will automatically be minimizing this. So why is that? Question: why does maximizing the elbow lead to minimizing DKL? Yes, because log px is fixed. Yes, that is correct. Because log px is fixed. Obviously, some people know variational inference already. So log px is fixed. What does that mean? Log px. Well, we can forget about the log. This is just a non-decreasing, it's monotonic function. So what we're interested in px, and px is just a distribution of our data. Our data, the MNIST images, for example, or the news articles. Our data joint probability, the total probability of our data, and that probability is fixed. It doesn't change, because no matter what you do on this side, the probability, the log likelihood of your data doesn't change, because your data set is fixed. So that is why, if this is fixed, then increasing, and you can rewrite this as log px equals DKL plus elbow, right? Plus elbow. So if log px is fixed, if this is fixed, then increasing this will automatically be leading to like decreasing that, right? So that's the whole idea. So question, no, is there any question? Like, this is a very important concept. This is the whole concept behind variation inference is this, that you start from DKL because you wanted to minimize DKL between Q and P. So you start from DKL and then you move the terms around, you arrive at here, and then you have an intuition that log Px is fixed. So instead of doing that, instead of minimizing this, you maximize this instead. So that would be easier. That would be easier because if you look at here, if you look at the two terms, if you look at the two terms inside the elbow, we do know QZ. We do know QZ because we were assuming that QZ is, for example, Gaussian. And we're going to stick to this Gaussian thing. So QZ is Gaussian, so you know the mathematical form. And PZ, comma X, which is the joint distribution of Z and X, this can be rewritten as P X given Z times PZ. And we were assuming that we knew this, the prior distribution, and we knew the likelihood. So we know everything there is to know to handle, like, play with elbow. Question from Woo-jung. Can you explain again why we use reverse scale divergence, not the original scale divergence? I mean, that's like a whole different story. But so they will lead to different stuff. So if you use PQ instead, then that leads to something called expectation propagation, and that would give you a Q that matches like the mean and the standard deviation of P, and that's like, it's kind of like moment matching, and that's not what we want. And so it's a bit theoretical thing, which I don't have a complete understanding to it, unfortunately. So let's stick to the QP thing instead. If anybody knows if anybody's like super familiar with expectation propagation, not expectation maximization, what we're doing here, QP is expectation maximization. If you're familiar with the Gaussian mixture model, GMM, then the way we update the parameter, the way we update the parameter, to learn the parameter, is by using expectation maximization, right? You derive the expectation first, and then you maximize the likelihood, and then you derive the expectation again. Like you do the iteration. So that is what DKL, that is what variational inference basically does intuitively. But that's what we are after. And PQ is not what is expectation propagation, is something else. So if anybody has like a great understanding of expectation propagation, you can share your knowledge on class. And I'm gonna have to mute everybody again. All right. We were here. Yes, we were here. And now, right, so the evidence lower bound. Yeah, so the great thing about this whole thing is that, so what we wanted to do is we wanted to learn PZ given X. So infer this. So that was our goal. But instead of inferring or estimating PZ given X, what we did is basically we're reframing this into an optimization problem, because all we need to do is just maximizing the elbow term. So maximizing or minimizing a function is optimization, right? So optimization is way easier than inference. Inferring this, basically. Inferring that is very difficult, but maximizing this is easy. You just do a stochastic gradient descent, and that's it. So yeah, so that's the whole setup. And the only thing that we have a control over in this elbow term is the terms involved with, or the parameters involved with QZ, which is mu and sigma of QZ. So because we already thought that, we already thought that PX given Z and PZ, they have a certain distribution. So this is kind of like a fixed knowledge. So all we can manipulate is QZ, and if this is Gaussian, then all we can play around with is mu and sigma. So what we do when we say that we want to maximize elbow, what we mean is that we want to tune mu and sigma so as to maximize this whole term. Then that will lead to DKL being minimized, and if DKL is minimized, then that means that Q and P are similar. Right. So hopefully the whole story makes sense. And sometimes people call this LQ. LQ is the variational elbow. Sometimes people call this variational free energy, and you can kind of see like why. Like if you look at this term, this is exactly entropy. So like sometimes people like interpret this as like an energy, like a thermodynamics thing, and then they call this like variational free energy. But this is just a side story. All right, so that's the whole gist of variational inference. And so far, any question? Like Woo Jung had a great question. Unfortunately, I didn't know the like an accurate answer to that. No question. Okay, so moving on then. So we took a look at the variational inference, and now we're moving on to VAE. So VAE is called the variational autoencoder is called variational autoencoder for a reason. So there's like a variational inference flavor in VAE. So if you look at the purely like a designing a loss function of VAE in that perspective is pretty much straightforward. So you have autoencoder. So VAE is still AE, so it's an autoencoder. So you want to compress and decompress. But there's one more condition that we want to satisfy. So which is that, so we compress X to Z, which follows certain distribution. So we want the latent space to follow a certain distribution. If you remember AE, that the latent space of autoencoder didn't follow, like there's no guarantee that it looks like certain distribution. There was like a bunch of dots, like ones here, there was like 7 and 4 in here, like there was like 8 here, 3 and 8 like all intertwined. You know, there wasn't a guarantee that the what kind of shape or what kind of distribution we would have in the latent space. It's just a space that is learned to maximize the compression decompression performance, and that's it. That's the only stipulation. That was the only condition that the latent space had to satisfy. But in VAE, there's one more condition, which is that we want the latent space to look like certain distribution. In our case, we want it to look like a Gaussian distribution. So that is it. So that is the only difference between autoencoder and variational autoencoder. That you want the latent space to look like a certain distribution. For example, Gaussian. So what we do is you can think of this as in a like a loss function term. But before that, we have to first define the encoder and the decoder. So this is the encoder. So we're going to call the encoder Q theta. So theta is the learnable parameters of Q. Like for example, Q theta could be Q theta of Z given X I. The ith sample could be just, you know, the same old function that we are familiar with, right? This could be a Q theta, and the theta being these two, the weight matrix and the bias, right? So that's Q theta, and P phi is the decoder, and again, it's the same thing. P phi being the decoder, the phi is the learnable parameters of your decoder, and you can see this is pretty much, you know, naturally like makes sense because the role of the encoder is that it receives X and then generates Z, which is a latent variable. The role of the decoder is it receives the latent representation of Z, and then reconstructs Xi. So that's the whole setup. And we, as I said, we want the latent space to look like certain distribution. So here it's, you know, it's naturally we want to use KL divergence because that certain the target distribution that we want this latent space to look like, we're going to call that PZ, and PZ is usually you know, standard Gaussian distribution N0I, right? So we want that, basically what this KL term means is that we want the latent distribution to look like PZ, and the latent distribution being this, obviously, because this is the encoder is the one that generates the Z's based on X's. So the latent distribution would be determined by the encoder function, and we want the distribution of the encoder or the output of the encoder to look like PZ, which is Gaussian. So that's it. So that's it. Yeah. So why do you want to do this? Why do you want to enforce the latent space to look like a certain distribution, in our case, P Gaussian distribution, then the reason is that if you look at this, so this is AE and this is VAE. So even AE is like pretty much well structured. It's not completely like Gaussian. There's no guarantee that it'll look like any distribution, but at least it's like, you know, there's like certain clusters, like we did with the like where the ones were here and the 3 and 8s were here. Like the latent space of autoencoder still is not completely unstructured, but what we want instead is we want to go from here to here. So why do we want to do this? Because we want to generate new samples. So if we have a certain guarantee that the latent space of your autoencoder follows a Gaussian distribution like this, then you can take this guy alone. So you only take the Z and the decoder. So this will be the decoder, right? This will be decoder. You only look at this part. You forget about the encoder part. You only take the decoder part. If you know that your latent space Z follows a Gaussian distribution, then you can sample a new point from your Gaussian distribution because you know that Z follows N0I. Then you can sample any new sample from your Gaussian distribution, put it through your decoder, and then that'll guarantee that the decoded or the reconstructed sample will look like a realistic sample because you know that your latent space follows the Gaussian distribution. So you sampled any point from the Gaussian distribution, and that any point, even though it's a new point, will look like a real sample, but not here. If you try to sample random sample from here or here or here or here, it'll look nothing like a realistic sample because this is out of distribution. Like this part, they are all out of distribution. You can only sample from this or this or this, then you'll get a real sample. But you don't know. You don't have a guarantee that you'll always be able to sample from this. But if you follow Gaussian distribution, then it'll look like this, and then you'll most likely sample from here, less likely from here, and less likely from here. So that's the whole setup. Right. Seeing no question. So that's yeah. So in perspective of the loss function, purely loss function, there's reconstruction term, and then there's a regularization term. So regularization term, if you're familiar with regularization term, there's usually like Ly y prime plus some, in our case, usually like L2, like L2 this L2 regularization term. You know, like in the second class, we were talking about how we can overcome overfitting by using regularization term, right? So that's the regularization term, like some term that is added to the original loss function being MSE or negative log likelihood. But the loss, this is the regularization term that regularizes the behavior of your function. So in the same manner, we want to enforce certain behavior on your function, which is that you want your latent space to look like a Gaussian distribution. So all we do is this is the reconstruction term. If you look at this guy, this is a reconstruction term because if you look at here, basically what it says is that this is the decoder's output. So this is a decoder, and decoder gets the Z and then reconstructs X. So this is the this part is the decoded output, and the log likelihood of the decoded output, we want to maximize it. And the Z which the decoder accepts comes from encoder. You can see that the Z follows the encoder's output distribution. So encoder obviously it gets X and then generates Z. So your encoder's output Z will be fed into your decoder, and then the output of the decoder, you want to maximize it. Basically, that's the reconstruction loss. So here is the reconstruction loss, and here is the regularization term. As I said, we want our latent space to follow a certain distribution, so we use KL divergence. So very, very simple. You just add one more term to your original autoencoder, and that's it. So that's the whole gist of VAE. Was there a question from Aldo? Could we do clustering with data with an unknown label using a VAE then? Could we do clustering with the data? Yeah, I don't think you can call VAE as a clustering algorithm. You can learn the latent distribution with VAE or with AE. Doesn't really matter. You just with VAE you learn a latent distribution, latent space that follows Gaussian distribution. With AE, you learn some other weird shaped latent space, and you can run clustering algorithms on top of this. You can learn you can run like K and N. I'm sorry, not K-means. Forgot the name of that. K-means. Sorry, yeah, K-means. So you can run K-means here. You can run K-means here, but VA itself is just an autoencoder with certain enforcing on the latent space. So I'm not sure if you can say that you want to do clustering with VA. VA is just a latent space approximator. Yeah, but as I said, once you've learned the latent space, you can run K-means or Gaussian mixture model, your favorite clustering algorithms on top of it. Hopefully that makes sense. All right, so purely from the loss perspective, it's a very simple one modification on top of autoencoder. But when you look at this and then you can interpret this in a more probabilistic manner. Okay, just one more question before we go. From 준영, A에서는 인풋 아웃풋이 같아질 로스만 있는데 B에서는 K-W처럼 다른 목적을 가지고 로스 추가하는데 그러면 VA보다 VA가 AA보다 성능이 안 좋을 수 있는 아주 좋은 얘기입니다. 당연히 그럴 수 있어요. 왜냐하면은 지금 요 스페이스는 이 인풋과 아웃풋 사이의 reconstruction. So the question is that because we've put certain regularization term on top of AE, might that lead to a suboptimal performance in terms of reconstruction as opposed compared to AE, because VAE has one more term? And the answer is yes, because if this was the optimal space for maximizing the reconstruction performance, then this is definitely not. And that means that your reconstruction performance could be a bit, a bit worse than AE. But that's a great question. But if you increase the size of VAE, then probably you can overcome that. Like if increasing the size of VA means that your latent space size Z being really large. It's not like 4-dimensional in our case. Maybe like very, very large dimension with very, very powerful encoder and decoder, then you can probably narrow the gap between the two. And that's what people do in diffusion models. With latent diffusion, like stable diffusion, they typically use VAE, but they don't. So another thing is that you can put you can put a trade-off term here, So that controls how strong you want your regularization to be. So if you want your latent space to be really, really Gaussian, then you can increase the size of your lambda. If you just want to put a small flavor, Gaussian flavor into your latent space, then you can downsize your lambda to maybe 0.1, 0.01, 0.001, something like that. Then it'll give you a slight structure in your latent space, not completely Gaussian, but slight structure. And that's what people do with stable diffusion. So very good question. Moving on. So this is purely based on the loss perspective, but if you interpret this in a probability perspective, we get a very nice understanding of what VAE is actually doing. So we go back from the inferring the posterior distribution. So we have an autoencoder. And this is the decoder part. And what we want to do, let's assume that what we want to do is like this. So this is X, this is Z, this is X prime. What we want to do is, let's say that we want to look at X prime or X, for example, like some sample out of your autoencoder, and we want to guess it's Z. We want to guess the underlying latent vector of that X. So that would be the inferring problem, right? So we start from this probability point of view. We want to infer the latent vector Z based on the outcome of your autoencoder. So this is the same thing. So if you remember this guy. So what this is, we started from DKL and then we moved some terms around. And this is before log PX being on one side and these two being on the other side. This is before that. So this is just a definition. And if you remember this, then the new KL for our autoencoder, our variational autoencoder to be more specific, is very much the same. The only difference between the two is that the Q is now QZX, not QZ. So this is QZ, and this is QZ given X, because our Z distribution depends on the encoder, which accepts X. So now the only difference between the two is that Q is now QZ given X. So now if you look at here, this is the only difference. The other terms are the same. They're the same. So yeah, like this. So we use QZ given X instead of QZ. That's the only difference. And obviously, the lambda here is the mu and sigma of this. Hopefully, I mean, we're going to assume that this is Gaussian distribution again, because we said the QZ is Gaussian distribution. QZ given X also, we're going to enforce that this is Gaussian, and because of that, we have two knobs to turn around, two parameters to play around with, right? So remember this, and then obviously what we want to do is oh, okay, we haven't gone there yet. Okay, so obviously we want these to be the same, and that means that we want to minimize the KL divergence. It's the same setup. Before in VI, we wanted to minimize this because minimizing this means that Q and P are the same. So we want to do the same here. We want to minimize this, and that means that minimizing the KL divergence, and the only knobs we can the only parameters we can tune around is lambda, which is the mu and sigma of this Gaussian distribution. So now we go to the familiar stuff. So we move this term here, just like we move this term here, and log px on one side, which is which was the constant. So minus this was the elbow term, right? This was the elbow term. So elbow term, right? Oh, sorry, the elbow term. Same situation. Minus this is the elbow term. So you can just see that there's minus here, then plus here, like this. So these two elbow terms are exactly the same thing. Instead of QZ, we have QZ given X, and there's joint distribution. And obviously, we would like to turn this into PX given Z times PZ, like before. So just like before, the VI, we wanted to maximize this elbow term. Now in VAE, we want to maximize this elbow term, right? And that's what we do. So as I said, we decompose into PX given Z times PZ, and then you take PZ to this part here, right? Because they both are the expectation of the same distribution, the Q. So we can, let me write it down. PX given Z, PZ, and then we take this Z and PZ into here. That becomes our KL divergence, right? And you're left with PX given Z here. So it's just moving terms around, so nothing in particular. And so again, so what we did is we started from the original, the KL divergence definition, and then we moved this term here, and we knew that the log PX is constant, so we can treat this negative this as a elbow term, and we want to maximize. So that elbow term is here, and we move the terms around, and we arrived at here, and we know all the terms here. We know that this is the encoder. I'm sorry. So this is decoder. This is decoder. This is encoder. This expectation over this distribution is encoder. We know that PZ is the standard Gaussian distribution. So all the terms we know. So we can maximize this, thus indirectly minimizing this. And then we would know that your encoder will estimate the true distribution of your of the PZ given X, right? So if you look at this, this oh, actually, yeah, there's one more thing I forgot to mention. So because if you go all the way back here, DKL, we wanted to minimize KL, and minimizing KL, we had only two free parameters that we could play around with, which was mu and sigma. But now that we arrived at this elbow term, there are way more parameters, because this P thing is a decoder. So there's like a theta. There was a phi. There's phi here, and the Q is actually is governed by Q function is governed by theta, And so instead of lambda, we say the Q is governed by theta, P is governed by phi, and these two things, the theta and phi, will be the ones that we can play around with to maximize this elbow term. Maximize this elbow term. So, yeah. Some people might wonder how we can forget about the lambda, which is the mu and sigma, and just completely replace it with theta. So what we do is we have an encoder. So there's like an image going in, like there's like an image of 9 going into your encoder, and that encoder will give you the encoder will be like a neural network. It will be like a multi-layer perceptron, for example, and at the end, you will have a 2 output from this multi-layer perceptron, which is mu and sigma. And then using these mu and sigma, you can derive a Gaussian distribution that follows this mu and sigma. So our encoder will no longer directly generate a z, like in autoencoder, we had this x, z, x prime. So in this autoencoder, the encoder directly gave you the output z, but here that's not what we're doing here. That's the encoder in the VAE will actually generate mu and sigma for this particular sample, and then using this mu and sigma, we can formulate a Gaussian distribution, and from here we'll be sampling z. So that's the difference between the two. So that's why we can say that Q is governed by theta, and P is obviously a decoder, so it's governed by phi. So you can rewrite this into this. There's like a theta and phi here. So this is how we arrived at the final elbow term when we started from the probability perspective, which is to estimate or infer the posterior distribution. But this happens to be exactly the same as the loss function that we talked about in like several pages ago, meaning like if you go all the way back here, this was our loss function, the reconstruction term and the regularization term, right? If you remember, if you keep this in your mind, if we go all the way back here, this was our loss function, and now there's one-to-one correspondence between this guy and this guy, and this guy and this guy. It's just that elbow we want to maximize, loss we want to minimize, so there's like negative plus, and this is plus and negative. So that's the only difference between the two. So you can realize that VAE's elbow term is maximizing the elbow is like minimizing the loss term, so it's the same thing. So we can, so once we arrived at here, the intuition is we should have an understanding that when we were actually, fine-tuning, when we were training our VAE according to this loss term here, what we were actually doing is maximizing the elbow for this inference problem, for this posterior distribution estimation problem. So those two are the same thing. So when training VAE by minimizing the loss, what we're actually doing is, in a probability perspective, we are maximizing the elbow. So that's the beauty of VAE. So we're not just willy-nilly, just, oh, I have reconstruction term and I just want to add a regularization term that enforces the latent distribution to be Gaussian. That is one way to interpret it, but there's more elegant, like interpretation that lies beneath this loss function, which is that you're actually maximizing the elbow term. Right, so and the elbow can be maximized by both, because there are two parameters, theta and phi. Theta being the parameters for encoder, phi being the parameters for decoder. So elbow can be maximized by both, but in reality, we just update both parameters at the same time. We just do an end-to-end gradient update. Right, so that's the whole gist of VAE. So any questions so far? So we could have gone straight from AE to VAE with, just by adding just the regularization term to the AE loss, and then that being it, that's it. But we took a detour by looking at the variational inference, because there's like this philosophy hidden inside. And that was the whole gist of the original paper, Variational Autoencoder, in 2014. All right, no question. I hope everybody is following along. So the one last thing is training VAE. So training VAE. How do you train your network? So we do have the final loss function. So we're going to forget about the elbow term now. We're going to stick to the loss function because we're training neural network. So we have a loss function. And how do we train our neural network? Our neural network being the encoder and the decoder. So before I just conveniently said that we update both at the same time, doing end-to-end create an update, but it's could be a bit, we need to dive into what that actually means. So this is the whole setup. But I can actually, let me write it down here. So we take an X. So let's assume that we're just sticking to one sample. This is just like pure stochastic gradient descent where the mini batch size is 1. So we only handle one sample at a time. So you have X from, so there's like a whole X's, like X1, X2, X3, like whole different X's. And we take Xi from here, right? And then we put it through encoder. Actually, let me write it down with a proper encoder, which is governed by theta, q theta, and then this will give you, as I said, this will give you mu I and sigma I for this particular X. And then using this, you can get a Gaussian distribution that follows this mu I and sigma I. And then from this, you get Zi, you sample Zi, and then using this, you get P phi. Okay, I don't like the shape of this P. P phi, and well, I should have written like this actually is no. So Q is actually, note that Q theta is follows this certain distribution, right? So the P theta is Xi given Z, and it'll give you, hopefully it'll give you back the Xi prime, which looks exactly the same as Xi. So, and you have the two loss terms. So based on this, you have two loss terms. One loss term is Xi minus Xi prime 2. So the reconstruction term. The other is DKL, obviously. So DKL being your Q, actually, it should be between your DKL between your mu I, sigma I, and Gaussian 0I. So this will be, so loss number 1, this is your loss number 1, this is loss number 2. And obviously we're using neural network. So we want to backprop, right? So we want to go, the things that we need to update is this guy and this guy. And we start from these two, the sum of these two losses. So sum of these two losses, I'm going to call the sum of these two losses just this thing. And what we need to do is we need to do this first, and we need to do this as well. Like we need this guy and this guy to update this guy and this guy, right? So that's the whole thing behind neural backpropagation. So can anybody see a problem here? Can we do end-to-end backpropagation and update the gradient, update the parameters? And if yes or no, and if no, why not? Yes, because of stochastic sampling. Yes, exactly. Sampling is not differentiable. So good answer. Sampling is not differentiable. So that's where this is the problematic side, this here. So up to here, no problem. Up to here, no problem, because this is all deterministic. The loss you can calculate, and then you can backprop the signal here, and then this is your encoder, this is your decoder, which is basically just neural network, and then you can update the neural network based on this. So this can be calculated. The problem is when you want to calculate this, you need the signals coming from all the way from the top to the bottom right here, and the problem is your signal cannot pass this stochastic sampling here, because as I said, your encoder will provide these two parameters, mu and sigma, and then based on that, you build a Gaussian distribution. From that Gaussian distribution, you sample Z, and then you plug that Z into a decoder. So there's a sampling part, and you can actually sample as many Z's as possible to be more specific. You can sample like 100 Z's and then get 100 output, get 100 Xi primes, because that's sampling. The problem is that the differentiation does not allow, it cannot pass sampling. All your steps must be deterministic in order for the backpropagation or the differentiation to work. So that's the whole thing. Right, so that was the good answer. So what we do is, before we move on to how we can bypass that limitation, certain things we need to check on. So sampling from your mu sigma, sampling from your Gaussian distribution that has mu and sigma as your the parameter, is like Monte Carlo's estimation of this. So as I said, you can sample many Z's, like 100 Z's from this process, but typically we don't do that. We typically we sample one Z and then we go with it. And these squares, we calculate the squared error here, so the reconstruction loss and the DKL. And fortunately, because these two are Gaussian distributions, you can end the KL divergence between two Gaussian distributions is analytically it's solvable. So it's very easy to handle. And on top of that, when your one side of KL is unit Gaussian, like standard Gaussian distribution with 0 and 1, then your solution, your expression becomes way easier. So if this is fixed and this is your parameter, so this is the only thing you get out of this whole KL divergence. So you can calculate this, and then you can start doing backprop with respect to we can go, you can do this and this. Well, not exactly this because of the sampling thing, right? So how about this? So the problem is that the reconstruction term involves a random sample Z, and the random sample coming from this, as I said. So the problem is that you cannot do a backprop because of the sampling process. So what we do, can you backprop through the encoder to obtain this? The answer is no. So how do you get past the randomly sampled Z? How do you get past this? Oh, where am I? Okay, so how do we get past this sampling thing so that we can update this? So when sampling is involved, there are typically two ways to handle this. One is actually three ways to handle this. One is using if the sampling is from the Gaussian distribution, you can do something called reparametrization trick, which is what I'm going to describe in a few seconds. Another thing is we can actually go for the reinforcement learning route. So that's another thing. And we can also try to approximate this sampling thing with a fixed a deterministic function and then go with that route. So there are a couple of options, but here we know that we're sampling from Gaussian distribution. So we take something called reparametrization trick. So here's the depiction of that. So your final loss, which is the reconstruction loss and DKL, your final loss is just this. And there's loss comes from your sampled Z. So this is a random node. So the circle is a random, your sample Z, and your Z is sampled from mu and sigma. And there's hidden things. Mu and sigma comes from your encoder, right? From your encoder. So you want to go from here to here and here to here so that you can update your theta. And because of this, there's a blocker here. So what you do instead is that if you think about the Gaussian distribution, the sample that follows a Gaussian distribution of certain mu and sigma actually can be rewritten as a sample that mu plus sigma, so Z equals mu plus sigma times a certain noise that follows where the noise follows a standard Gaussian distribution. So they are the same thing. These two are These two are the same thing. So if Z follows this, then Z can be rewritten as like this. And the only stochasticity or the randomness comes from the epsilon, which follows this standard Gaussian distribution. So this is what that depicts. So instead of having your Z being random, you set aside the randomness to this other node here, which follows this epsilon follows Gaussian distribution, standard Gaussian distribution. That was I, not Z. So now you can safely backprop all the way back to your Q theta. So there's nothing that blocks your backprop, chain rule from starting from lambda, the loss function, not lambda, sorry, your loss function all the way back to theta here, because your randomness is put aside to this this node here, and now your theta has nothing to do with from your theta to the loss. There's nothing that there's no randomness in between. So that's the reparametrization trick. So instead of sampling Z from your Gaussian distribution, you calculate Z based on mu and sigma, and then you just sample one random noise from a standard Gaussian distribution, right? So this is called the reparametrization trick. So the whole picture looks like this. So the whole picture looks like this. So you have two losses, reconstruction loss and your KL divergence loss. So that becomes your combined loss, and your KL divergence only depends. So interestingly, your KL divergence loss, which is this, has nothing to do with randomness, because this mu and sigma comes straight out of your encoder, right? So there's no sampling or anything at all. So your KL divergence loss didn't have any problem with randomness to begin with. It was the reconstruction loss that had the problem with the randomness. So this diagram makes it a little bit clearer. So your KL divergence loss only depends on the output from the encoder. So straight you can calculate the loss directly, and then Z depends on now, because Z is now mu plus sigma times epsilon. Now there's three things that goes into Z, and then the Z is fed into the decoder, and then the decoder generates the reconstruction x prime. So that's how you get MSE. So now everything is working perfectly. Everything starting from your loss, you can calculate from this guy all the way to here, and starting from your KL divergence loss, you can go all the way here, and you can do an end-to-end parameter update. Right. So hopefully this makes it very clear. Any questions so far? The rest is just a few visualizations of the latent space. Yeah, I'm guessing there's no particular question. Okay. Let me give you some visualization examples, and we can end the class that. Question from Aldo: why use mean square error instead of binary cross entropy? Because your MSE, your MNIST digit, when you convert it to a vector representation, the values lie between 0 and, well, actually it could lie between 0 and 255, which is pixel intensity. But you can normalize it to 0 and normalize between 0 and 1. But still, it's not binary value, right? Your pixel values are kind of like continuous. So you don't use binary cross entropy. You can use binary if your data set is a binary variable, then you can use binary cross entropy, but we're using like images here, so that's why we use MSE. You can use L1 as well, but that's a different story. All right, I'm hoping that answers your question. So let me share a new screen here. So this is how latent space changes as you run your VAE. So yeah. So you start with a very like randomly just mushed together latent space, and now as you run your, this is MNIST, so you can see like 0, 1 to all the different digits. So now they're like looking for their places, and the overall shape is kind of like, I mean, especially for each digit, they are certainly like spherically shaped, and the overall shape is like kind of like spherically shaped. Question. I'm trying to understand why autoencoders in papers use a cross-entropy list. I'm not really sure. Yeah. Autoencoder is just it's just an idea. You have an encoder and decoder. You want to maximize the reconstruction loss, and what kind of reconstruction loss you want to use, that's up to you. You can use MSE loss. You can use L1 loss. You can use maximum likelihood. You can use like cross-entropy loss. That's totally up to you, and it depends on what kind of data you use. But the idea of autoencoder is very general. You can use whatever loss function you want to use. And as I said, you can add more regularization terms, such as in sparse encoders, you can use sparse inducing regularization term. In VAE, you can use KL divergence as your regularization term. There's a lot of different variations. So this is how the latent space changes. And interestingly, this is what happens when you, so let me see if I understand this correctly. Yeah, so what's happening here is that, let me annotate. So you can think of this as a grid, two-dimensional grid. What the author of this blog did is he or she, I'm not sure the gender of this person. So the author trained an autoencoder using MNIST digit images using the latent space size of 2. So the size of Z is only 2. So you can assume that the Z lives in a two-dimensional space. And this is your origin. This is -3. This is 3. And this is this is 3, and this is -3. And what the author did is he or she moved around this latent space, and then sampled from there. So there's like Z here, there's Z here, Z, like there's like Z's everywhere in this the range between -3 and 3, this grid like world, this square grid like world. There's Z's everywhere. And what he or she did is they sampled the Z's from this space and then try to visualize it, every single one of them. And as you train your VAE, the visualization quality becomes better and better now, because in the beginning it wasn't learning anything, so it's just purely pure noise. It's just pure noise, like here, like pure noise. But now as you train your VAE, each region in your grid world, each region is responsible for a certain like digit. Like this part is all 0, this part is all 9, this part is all 1. It's still 1 here. I think there's like slight 8 here somewhere. And you can see that this axis, the x-axis, kind of is responsible for the angle of 1. Like the only thing that changes along this axis is the angle. The semantic doesn't change. Digit 1 doesn't change. And I guess like here, there's some semantic changing. Right. So anyway, this is like a good way to visualize what's happening in your latent space as you train your neural network. So going back to here, back to the final slide. Actually, I can just use my PowerPoint. So the final conclusion: the VA is an elegant solution for approximating the posterior distribution, and it is still an approximation. So it's not like you're estimating PZ given X. It's not true PZ given X, right? So there's this again, it's like variational inference. And the two mapping functions are disconnected. So there's like a certain caveat. So when I say that the two mapping functions are disconnected, yeah, I should actually get back to my iPad too. How do I screen? So two mapping functions are disconnected. That what does that mean? That means that there is a lag. I'm not sure why. I think it was better than this. Does anybody know why I get a lag like here? Like I think before it was very smooth. We are at the end, doesn't really matter. Anyway, so the two mapping functions are disconnected. The two mapping functions meaning the encoder and decoder. And what does that mean is that the encoder and decoder use separate parameters. So, for example, you have a certain x distribution, the distribution of x, and you have a latent distribution, which is usually z, right? And then you have a output distribution, x prime. Okay, I'm going to call this x prime. So this is the encoder, q theta, and this is the decoder, p phi. And because these two encoder and decoders share nothing, they share nothing. Their parameters are not tied together. It's just they are separately trained. It's just that overall they want to maximize the reconstruction loss. So because of that, if you pick a sample from this spot and then you using the q theta, you map it to right here in your latent space, this Gaussian distribution space, and then taking that, you use p phi, the decoder, to map it back to the original space. There is no guarantee that these two places will be the same. Like they could be completely off, you know, like the p theta could map this z to completely different spot, which happens to look similar to this guy. So there's no guarantee that these two will be exactly the same. So that's where the two mapping functions are disconnected. So because of that, some people thought this as a limitation because there's a disconnect and there's no guarantee that these two are the same places. So what they did is they come up with something called normalizing flow. So normalizing flow uses a invertible function instead of two different functions. So here, instead of using q theta and p phi, they use some f and f inverse. So that will guarantee that this guy will go back to this guy, which is exactly this guy. So that's the whole idea behind normalizing flow. And yeah, if you're interested, you can study normalizing flow. And there's like different variations, beta VA and TCVA. They are like how to disentangle the latent dimension of z. Like you want the first dimension of z to be responsible for the angle of your digit. The second dimension of your z to be like the thickness of your digit. The third is like semantic. You can like disentangle you can try to disentangle the latent space for each dimension by dimension. So you can study these if you're interested. They're like very, very old ideas, like 2015, 2016. There's like the whole VAE advances after like 24. VA came out in 2014. Now it's 2013 and 2023. So it's like 9 years. So it's like history now. So the important thing is that you understand the basic, the foundational idea of VAE and the reparametrization trick. Reparametrization trick is used very, very often in like Bayesian neural networks, and every single time you need to sample from a normal distribution. Yeah, and yeah, you can do a lot of stuff with VAE, like generate sequences or graphs, but people usually these days use diffusion models to generate stuff, especially generating images. For generating sequences, people use transformer, but the connection between VAE and diffusion is also a little bit interesting. So we'll get to that at the end of the semester. All right, so I think this is it. There was a question from Han Songju. How can you validate the generated data, especially when the data is not an image? Although image can be distinguished visually, I think it is difficult to determine whether the new data has been generated successfully. Yeah, that's a good question. Generative models always suffer from the same problem. Like, how do we evaluate whether the generated samples are realistic samples? Like you said, images, people can look at it, but the problem is that people cannot look all the images generated from your generative model. So people use some other metrics such as FID, or there are some scores people use. So, but if we're dealing with certain things like text, like ChatGPT is a generative model, and if you ask it to generate a report, like 400-word report on variational inference, then you can generate as many samples as it wants. And how are you going to evaluate whether they're like actually good reports? You can't read all of them at the same time. So you can do like a certain indirect evaluation whether their word perplexity is like low enough or if their word frequency is like similar to academic journals, you can do stuff like that. But at the end, somebody has to read the generated report and see if it makes sense, and if it's talking about VAE, and if it's consistent. Like somebody has to do it, and somebody meaning like people, and it's not scalable. So there's not a good way to. There's no I don't think there's a good like definite way to evaluate generated samples and see if your model is doing a good job. It's only episodic. You sample from generative sample, like 100 samples, 200 samples, and you give it to qualified individuals, and then you ask their opinion. If they say it looks good, then based on surveying, it seems good enough. Like, it's basically surveying, like when you want to estimate the average height of Korean people, Korean male or Korean female, you can't go around the entire nation and like measure the height of 50 million people. You randomly sample from certain regions, and then maybe 100 people, like 100 people, and then you estimate the mean, and that's it. So kind of like that with generated samples. You can't evaluate every single sample coming out of generative model. So you sample, and then if it's good enough, you assume that it's good enough. Hopefully that answers your question. Cool. All right. So as I said, this Thursday, the TA will be conducting the VAE, the practice. So please come if you have time, if you're around, because you'll be able to practice the reparametrization trick. Question: could we use VAE to figure out the latent distribution like AE or DAE? What's DAE? Denoising autoencoder, I guess. Use VAE to figure out the latent distribution. I guess the assumption of normal distribution make themselves get away from the two relations. 그렇죠. 네, 더 벌어질 수 아니 이제 A랑 DA랑 다 결국에는 주어진 데이터만큼만 배울 수 있습니다. 그러니까 이제 A도 그렇고 DA도 그렇고 결국에는 사용자가 주는 데이터를 최대한 잘 압축 해제하는 스페이스를 배울 뿐이에요. 그렇기 때문에 이제 전 세상 데이터 다 모아야지 정말 트루 디스트리뷰션을 배울 수 있겠죠. 근데 뭐 그럴 일은 없으니까. 그러니까 그거랑 별개로 그래서 이제 VA를 쓰면은 VA는 오히려 더 레이트 스페이스가 가우시안이 되도록 강요하기 때문에 뭐 A랑 DA의 디스트리뷰션을 VA로 배운다는 건 어떻게 보면 말이 안 되겠죠. Yes, please, if you have time, you can please read Classum. And, as I said, I've already made the announcement on Classum that during the holiday season, I'm going to do as usual. So before asking me questions, please read Classum, because most of the important stuff are already on there. If 400 people ask me the same question, I don't have the time to answer them individually. So as I said, you don't have to come. Like, you don't have to come to any class the entire semester, because the videos are all there. The learning materials are all on Classum. So if you're interested, you can come. Any question before we end the class today about VAE? It's interesting because last time in AE, there were a lot of questions after the class, but now that VAE is, I guess VAE is like extension of AE. So that's why already, hopefully people already have a pretty good understanding, and that's why there are no questions. Okay, so I'm going to end the class today. So if you do have questions, always ask on Classum. And as I said, during the holiday season, during Chuseok, the Thursday practice session, the next Tuesday theory session will be conducted as usual. So if you have time, please come around. If you don't have to come as usual. And I'll see you guys next Tuesday. So happy holidays, everybody, and happy weekends. Yeah, thank you. 네, 감사합니다. 감사합니다. 네, 감사합니다. 네, 추석 잘 보내세요. 네, 감사합니다. 네, 감사합니다.